Let's watch along with Ben Eater for a bit about his debouncing circuit.
There it says 1 MFD on it, but apparently these are 2 microfarads. But anyway, the nice thing about this is 1 mega ohm is 10 to the 6th, and microfarads are 10 to the minus 6. So the math works out really easily here, so that a 2 microfarad capacitor, when you multiply it together, you just get 2. So that gives us a 2-second delay. And sure enough, we push the button, the LED stays on for 2 seconds, which I guess is further confirmation that this 1 MFD capacitor is really 2 microfarads. Anyway, so 2 seconds is kind of long for what we want. So what we could do is we could put in a 0.1 microfarad capacitor instead of this 2 microfarad.
This is for shifting the clock frequency. The previous video is about how you generate the clock. And it turns out to be just an RS flip-flop and 2 comparators. I hadn't actually watched that video when I made that circuit, which is an RF flip-flop and a buffer, but I drew something the other day about generating random numbers. No, that's that circuit. It's another circuit. No, I can't find it. Doesn't matter anyway. That's on the push down list. So is this. That was trying to do differential forms and Freyer-Holmer's thing. Yeah, it was that. But the point is that when you work with analog systems, you don't need to understand the, how do I say it? You're quotienting phase spaces rather than particular characteristics of systems. You're not formalizing particular behaviors. You're trying to understand the whole. You're trying to work with the whole system.
Capacitor, and if we stick that 0.1 microfarad capacitor in there, that's going to give us 0.1 seconds because we're multiplying it by this 1 meg ohm resistor. So now it stays on for 0.1 seconds. No matter how quickly I push it, it's kind of hard to tell. But that's what we want. We want it to pretty much follow what we're doing when we push the button. But we critically are getting rid of those bounces. And so as long as any bounces that happen within the first 100 milliseconds or 0.1 seconds, we've gotten rid of. And that's what we want. And so to understand how this works, let's look again at our circuit diagram. And I've got the 555 timer here, the guts of it exposed here. But the green bits out here are our circuit. And of course, we have an LED hooked here, the output I didn't draw. But and of course, we're just looking at this lower half here. This is what we built in the last video. And so we've got our resistor here, which is our 1 meg ohm resistor. Then we have our capacitor, which is a 0.1 microfarad capacitor.
Those
and then
555s are fun. I get a lot of mileage out of hooking just 2 or 3 of them together and synthesizing sounds when I was a kid. I had this idea when I was on the street, on the corner of the street in Cochabamba, the one opposite the Korean cafe near Plaza Constitution. About what you could do with networks of cells like this on an FPGA. So that you could program them. When I saw that absolutely great extracting the operational semantics of a 6502 processor from the die, from a photograph of the die, the production die of a chip, because it's a simple enough process, it's got few enough layers that I think from just the photograph. Let's see if I can find it. 6502. That 6502 song is great. You can take these old 80s game machines, any old 6502 processor, and stick a Raspberry Pi in instead of the EEPROM. And then you can have a very high bandwidth I/O onto the 8-bit system. That's real protest. There's an operating system for Ben's 6502 computer. That's different to his 8-bit computer. This was a lovely little thing. A long time ago, somebody wrote a 6502 simulator in 6502 assembler. Let's watch a bit of that. Now we're going to get adverts. Innovation is in their DNA, designed to inspire, created to excel all limits. Intel Avo. Now we've got 2 minutes 41 of some commercial for Fairy Liquid, which is bigotry. I can't skip that ad for YouTube, so I'm just going to reload. I'm not going to watch 2 minutes 50 seconds of Fairy Liquid adverts.
Hello and welcome to Programming Like It's 1979. Today we're going to look at a 6502 simulator that has a bit of a mystery attached to it. Now, I actually used this as the backdrop to one of my assembly language programming videos. And someone saw it and said, hey, what the heck is that thing? And that's exactly the reaction I wanted, because this thing is crazy. It's on.
I remember that noise. I love that noise.
With the name Apple 6502. That's it. .disk. You could find it on archive.org, and all it has is this one program. There's no identifying information. There's no here's who wrote this. It's just this program. So let's run it and find out what it does. Okay. So first it asks us if we want to load a program from disk. Let's say no. And then it asks, do we want to type in some code? Well, I don't know how it wants me to type in code, but let's give it a go. I prepared a very short assembly language program here.
Let's skip.
Let's look at it. We've got some breaks there. Okay, Control Y. Here we go. At what address do we want to begin tracing? Well, we wrote our program at memory address 800. What the hell is going on here? This is amazing. We can see we're loading the value.
That was a long time ago. I'll put the link in the description. Emulating a 6502 in JavaScript. This is related. The JavaScript was extracted from a simulation of the electronic level, and I mean electronic level of the die.
Only needs 1 extra byte. This guy's AD, and he needs 2 extra bytes. So if you're using the 0 page, it's slightly more efficient. Then we get graphically shrunk down to sort of this size, which is, I just think, unbelievable. I mean, in my day job at the moment, we do a little bit of like FPGA development type stuff, and the tooling behind that is amazing. But just the thing that human beings were doing this is just incredible. If it's not, when it's not naked. Oh, hang on a second. I have just had an Ubuntu thing pop up on my screen. There we go. When it's not denuded of its plastic case, it looks like this. It's got thousands of pins on the outside, but it's actually just a tiny little thing in the inside of there. So these chips are important because in the 1980s, the 6502, along with the Z80, was responsible really for the 1980s boom in home computing. It was an affordable chip. It was powerful, and certainly for me, it was. It came at the time when computers were sort of picking up, and I suppose directly led to me being here in front of you, becoming a computer programmer, and I'll talk a little bit more about that in a second. So I actually contacted over Twitter the people who still have the patents and the rights for the 6502, and I said, have you got any idea how many of these are in existence? Thinking it would be a few 100,000. I'm thinking how many computers with them there have been made, maybe 100,000, maybe half a million or something, but apparently more than 10 billion of these things have been produced by just one company. So there's probably much more than that out there. It's pretty incredible. So
10 billion chips. One of the companies is in Mexico. So that's not it. That doesn't reference that. I got confused. And it looks like I don't have the video in my YouTube history anymore. So let's try 6502 reverse engineering. This is it.
You've got the eye.
How long is this? 15 seconds. Well, thank you, Ella. I can't skip this either. This is another half a minute.
Okay, welcome everyone. The next talk is about reverse engineering of the MOS 6502 CPU that was designed for the Apple II, the NES, or the C64. And I hand you over to Michael Steil, who will present you everything. Thank you.
Hello. As you just heard, the name of my talk is Reverse Engineering of the MOS 6502 CPU. My name is Michael Steil, Michael Steele. Fans, yay. Subtitle is 3,510 transistors in 60 minutes. Let me just get some quick overview of the audience. Who of you has written any assembly code ever, any architecture? Ooh. Okay. Who has not written, who doesn't know what assembly is? Okay, that's good. That's useful. Who has written 6502 assembly before? Okay, so don't feel bored in the first 10 minutes. Who has ever implemented a 6502 emulator or re-implemented 6502 in an FPGA? 1, 2, 3, 4. Okay. Who has been part of the original design team of the 6502 in Pennsylvania? Okay. No liars in this audience. Okay. So for all those who don't know about the history or don't know about all these things about the 6502, there was this company MOS, which was founded in 1974, all by people who quit Motorola, who had been working on the 6800. This layout engineers cutting rubylith, that's some kind of plastic foil, cutting the actual every single transistor. Recently, there's a couple of pages. It seems to be the complete schematic diagram of a 6502, but it doesn't seem to be the original. It doesn't. It's some original schematic diagram from the 6502. He doesn't say how he got it, but it looks really good. It's rather really, all not complete, but the question is, where would you look if you wanted to reverse engineer something properly? You wouldn't try to steal the source code or get the source code from somewhere. You would look at the actual thing, right? So people have done die shots of it, so this is a very early one, and everything people could understand about it was, well, there's some decoder, some logic, and registers. That's everything that was understood about the die shot. In 2001, some guy with the first name of Balázs from Hungary take really nice high-resolution photographs of a 6502 with some old Russian microscope, all black and white, but really great. And he did a lot of work reconstructing every single transistor and drawing this schematic diagram, which is complete and has every single transistor. And he did that all by himself and alone in Hungary, and then wrote a paper about it, all in Hungarian, So some people, he was translated. Some people translated some parts of what he wrote and tried to understand, because I understood a lot about what was going on in the 6502 because of what he had learned from copying all those gates. But there were some other guys, Greg, Barry, Brian, and Ed, who just recently, so last year, they started about 1.5 years ago to do the whole thing again and properly and very high quality and debugging everything and making sure everything is completely correct. And these are the guys from the Visual 6502 project, which you have probably seen. So I'll tell you a little. So originally Ed was supposed to be here and do part of these slides. So serious hardware for that, really good microscopes. What Greg did was take lots and lots of tiny photographs and then stitch them together. So one of these photographs would be this one. It looks all really nice. But just taking a photograph of just the surface wasn't enough, because a lot of manpower you get from this photograph to this completely digital and really nicely colored representation. So if you look at the intersections of all these traces and at what layers, at what levels they are, and understand NMOS and how this processing was done, from that you can derive the net list. And the net list is basically all the transistors and how the transistors are connected and how the nodes are connected to the transistors. And on the outside you can change pins. For example, you toggle the clock switch. And then you have to look at all the nodes that are going from there to all the transistors. And you have to look at what the potential of these nodes is, and they have to share all the same. Emulator would be, you write it, it's not the original code, it's just a copy, it's just a re-implementation. The thing here is, you don't really, if you need to get it more complete, you need to add a little more of data, but a lot more of code. It gets a lot more complex in code. If you do this with this netlist approach, the emulator, which emulates physics, is always the same. It's just a couple of hundred lines of code. And you just add more polygons, you just add more data. So with an emulator like that, you can emulate a 6502 or any other CPU done in the same processor. It doesn't even have to be a CPU. So I told you it was pretty slow. What do you do if you want to get something even slower? You write it in JavaScript. So here's the whole HTML5 goodness of the Visual 6502 simulator that those guys did. I wasn't involved in that.
So that's what I mean by quotienting phase space and producing the digital semantics of it. There are other things you can do with those micrographs. You can if you had efficient physics simulators, you could simulate them at cryogenic temperatures with very low voltage, and you might be able to get a kind of multi-phase gig going on the physical silicon. And you may be able to, you will be able, that will set up certain boundary conditions which ought to allow you to do something with that chip more than just running it at 1.1 megahertz. What that is depends on your ability to discriminate between these quotients of the phase space. So that's the level at which I was thinking you could go with this type of approach to computation and semantics. Good video, that one. Fantastic.